Today we're starting a unit on circular motion. There are lots of things that move in a circle in the universe. For one thing, the moon moves in more or less of a circle around the Earth. The Earth is going in a circle more or less around the sun. Electrons move in a circle around the nucleus in the Bohr model of the atom. So we got big circles and little circles, but the motion in these examples is all very similar, and that's what we're going to be learning about. In class, we're going to be doing a lab using an eraser that's tied to a string. The string goes through a plastic tube, and at the other end of the string is a weight. And you are going to be twirling the eraser over your head and measuring the speed. And here we've got circular motion. The eraser is going in with a constant speed, but the velocity is not constant. In this case, because the direction of motion is constantly changing, and we know that velocity is a vector quantity, if the direction is changing, the velocity is changing. And if the velocity is changing, there must be an acceleration. That's what we're going to be learning about today. That acceleration in circular motion is called centripetal acceleration. Centripetal means center-seeking. So for instance, if we've got our eraser moving in a circle, let's say the eraser is right there at this initial time, and it's got a velocity in this direction. Here's my initial velocity vector, and that's an I for initial. And then a little bit later, let's say right here, the eraser is there. The velocity is in this direction. It's the same length, has the same magnitude, it's going at the same speed. And that I'm going to call our final velocity. So to find the acceleration, the direction of the acceleration, we can look at these two vectors. And one way to think about it is if we put the two vectors tail to tail, like that, then the change in the direction, change in the velocity is going to be this. This is our delta V. So this is our initial velocity, final velocity, that's our change in velocity. To do that a little more rigorously, we can see that we know that delta V is equal to final velocity minus initial velocity. And if we're going to be subtracting vectors, what that means is we're going to be adding the negative of the initial velocity. So in this case, I'm going to take my initial velocity, which is in this direction, but I'm going to make the negative, I'm going to change the direction. So this is my negative initial velocity. And then the final velocity is this one. We're going to keep that in the same direction since we're not making it negative. And we're going to add them head to tail. And we know when we're adding vectors head to tail, then the resultant, the sum, is what we get by going from the tail of the first vector to the head of the second vector. So that's our delta V. So we can see by either of these derivations that the direction of the change in velocity is toward the center of the circle. And as we know from our previous studies, acceleration is delta V over delta T. And so the acceleration is going to be in the same direction as this delta V. And so we call this center-seeking acceleration centripetal acceleration. We have a subscript C for centripetal acceleration. And then we know from Newton's second law, F equals ma, that there must be some kind of a force also in the same direction as this acceleration, and that we call the centripetal force. So whenever we've got circular motion, there is a centripetal force pulling our object toward the center of the circle. And so if we think about the moon, what is pulling the moon toward the center of the circle? In that case, it is the gravitational pull of the Earth. So that's what we're going to be learning about in this unit, and we're going to be doing a lab in class today.